Okay, I guess everybody is here, so we can start again. So 3, let's try to have a proof, or a sketch of proof of exponential decay for easing. So the theorem is going to be the following. Stated as such, it's brand new, but of course, it was known for a long time, in particular by Eisenman, Barsky, and Fernandez. And the theorem is saying the following. For beta smaller than beta critical, if I look at the sum, so I'm looking at the Ising model, right? So the sum of a ZD of sigma 0, sigma x, this quantity, which is sometimes called the susceptibility of the model, is finite. So, this is not really exponential decay, but remember, we have long-range interactions. So you cannot even expect exponential decay in general, right? Because just you can imagine, if your long range is, for instance, decaying polynomially fast, you will have a lower bound, which is going to be... So sorry, I should remind them. So jxy is a function, especially that it was during the first lecture. Sorry about that. So it's a function of x minus y. It's translationally invariant, and it's positive. That's the two assumptions. So in fact, you can see that there is a hidden... Exactly. So there is a hidden assumption, which is that if you want beta, the critical value, to be of any interest, and in particular non-zero, because if it's 0, it's not so interesting, you need the sum, in fact, of the jxy to be finite for every y, for every x. So sum of a y of jxy finite. So then everything equal to 1 will give you beta c equals 0. But a priori, you can have this, and some of the properties will just be true even for beta c equals 0. But for us, what is interesting is this regime. So for beta smaller than beta critical, if jxy is finite range, so finite range just means that if x and y are a distance more than, say, a certain r, which is the range of the dynamics, then jxy equals 0. Then in this case, you really have exponential decay. Then there exists a C, which is a C of beta, such that mu free beta sigma 0 sigma x is smaller or equal to exponential of minus C times the distance between 0 and x. Just notice that here, since you know it's positive, you only need that, and maybe let's just take distance to be like that. And the third property is for beta larger than beta critical, so then, of course, I have ordering. And what I can do is I can look for the press boundary condition at the spin at 0. Okay? So the magnetization of my model. And what I expect here, what I can prove is the following, is this bound. So remember, for percolation, the proof that we provided was proving that the percolation probability that if I look at this quantity and I look at P larger or equal to PC, the proof that I provided was proving the following inequality. That for P larger than PC, so let's put something like that. For P larger than PC, the growth is at least linear. And in fact, this linear growth is the mean field bound. If you take percolation in mean field, or if you take percolation in very high dimension, this is the actual growth. You grow like P minus PC. If you want the critical exponent is 1. Well, this is the mean field bound for the Ising model. If you take the Ising model on in mean field or in very high dimension, the growth is, in fact, here you see it's square root of beta minus beta critical. So the exponent is 1/2. So the proof is going to be very much reminiscent of the percolation thing. And, I mean, kind of surprisingly, it gives you also the mean field bound for the Ising model. So I think now it's fair to say that this is a unified proof for Ising and percolation. Let's try to at least give you an idea of how you prove that. Let's start for beta. So it's going to be exactly like for percolation. We are going to introduce a quantity. So if I take a subset S which contains 0, a finite subset of ZD, I'm going to define phi beta of S. Or maybe I should, let's just go there to have more room. So for for a set S containing 0, define phi beta of S to be the sum for x in S, sum for y not in S of sigma 0 sigma x. I'm going to explain all of this, don't worry. And here I'm going to take the hyperbolic tangent of beta jxy. So let me simplify a little bit. Imagine its nearest neighbor. Okay? Imagine the model is nearest neighbor. So I have a set S. I have 0 here. So I'm just counting when I'm saying x and y, and I'm saying that I take the tangent the hyperbolic tangent of beta jxy. Since if x is not a neighbor of y, jxy is going to be 0. This thing is going to be 0. So here I'm just summing over x in S and y not in S but neighbors. So that's what I call delta S in the proof of exponential decay of percolation. It's the edge boundary of your graph. And for percolation, I had a P here. It was P times the expected number of points on the boundary, which was connected to 0. Well, here the P is replaced by this hyperbolic tangent. And the probability of being connected to 0 is replaced by this spin-spin correlation. But otherwise, it's exactly the same quantity. Sorry. Okay, so this is the same intuition, same quantity. So now we define beta C tilde to be the infimum of the betas such that there exists an S. There exists an S with phi beta of S strictly smaller than 1. So we do the same thing as for percolation. And now I'm just going to sketch what is going to be the proof. I'm not going to explain it completely, but now you want to prove that for beta smaller than beta critical, beta C critical, you have exponential. Say, let's take nearest neighbor. Let's take nearest neighbor. So I have exponential decay. And how do I prove that? Well, you remember for percolation what I did, I took so I choose S with phi beta of S smaller than 1. And for percolation, what I was doing is I was saying, so there is this set S, I have 0 here. If 0 is connected to the boundary, or to a point far away, there must be a path from 0 to some boundary point in S, and then a path from this boundary point to X. And I was using some conditioning, which was basically just hiding the BK inequality, to say that it was smaller than the sum over the point here of the probability of being connecting times the probability of being connected there. But if the sum of the probability of being connected on every of these guys is smaller than 1, when I was iterating, I was getting a certain coefficient smaller than 1 to some power. And that was giving me exponential decay. Well, here, what can I do? I can do exactly the same. I can just say, if I want this thing, well, it's smaller by Simon's inequality, smaller than, let's take Z here. It's smaller than the sum over y over x in what do I want to do? In let's say the internal boundary of S of mu free g beta of sigma 0 sigma x times the same quantity sigma x sigma y. Okay? This is just Simon's inequality because S, since it contains 0, I mean the boundary of S is by definition disconnecting, I mean separating 0 from y. From Z, sorry. Yes, I mean, okay, now I see that I'm getting tired. Sorry, thank you. And now you see, just imagine that this is typically just depending on the distance. Okay? Then what did I do? Here I explicited this. I mean, if it depends only on the distance, or if, let's say this is constant. It's not constant. Well, just there. That's bound by the maximum over x in the boundary of S of mu g beta free of sigma x sigma z. And then I get this quantity, which is almost like phi beta of S. Except there is this tangent, this hyperbolic tangent here. Let's forget the hyperbolic tangent and let's say it's phi beta of S. Okay? So you get phi beta of S. So now what you get here you can see that x and z are at least distant distance between x and z is larger than distance between x and between 0 and z minus the range of your dynamics. So let's say R. So now if you maximize, basically what you get is that the biggest correlation at distance, say L, is smaller than phi beta of S times the biggest correlation at distance L minus R. And you can iterate that, so it gives you phi beta of S squared times the biggest correlation at distance L minus 2R, and so on and so on. So you get that this thing is smaller than phi beta of S to the L divided by, distance divided by R. So I'm just sketching here because it's very much, it's very close to the proof for percolation, so I don't want to redo it completely because I would not have time. But basically, that's the same thing. So here, of course, I cheated only once, which is saying this is phi beta of S. I forgot this hyperbolic tangent. But in fact, the decomposition here, you can do it a little bit better. Instead of saying 0 to x and then x to z, you can just use also you can use x inside and y outside. And then it's really phi beta of S that goes out of the computation. It's exactly this quantity. So this quantity comes out to make this thing work. So just to remember, for percolation, you have a proof using the BK inequality. The equivalent for Ising is exactly the same proof, but using Simon's inequality. In fact, an improved version of it, but it is basically Simon's inequality. Now let's try to do the other inequality. So let's try to get that for beta larger than beta c critical, I have a bound which is of this sort. So of course here I did exponential decay, but in fact if you are careful you can just do susceptibility in infinite range. There is no problem with that. So let's try to get this now. So remember, for percolation, just parentheses, the idea is that you could prove the following thing, basically. That this thing was larger than, or this thing was larger than the infimum of the phi p of S for S containing 0 and included in lambda n times 1 minus the probability of 0 connected to the boundary of the box. This was the differential inequality that we were using. So for p larger or equal to pc, this thing was larger or equal to 1, and you were getting the derivative of something larger than 1 minus, well, there was a 1 over p here. But, you were getting that. So if this is larger or equal to 1, you can just integrate this thing between pc and your p, and you would be getting exactly the inequality you wanted, this inequality. And then what you were doing is you were letting n tends to infinity, and you were getting the same inequality for 0 connected to infinity. So that's where it came from, this differential inequality. I mean, from a thermodynamics point of view, this is very natural things to do, these differential inequalities. You are trying to get differential inequalities between thermodynamical quantities. It's, usually they are more complicated than this one. This one is surprisingly simple, but it's a very natural thing to do, in fact. It doesn't, it's not something weird. So what do we want to get? Well, in our context, we are going to get the same thing, but we want to replace the percolation by something else. And what is this something else? Well, this is exactly this p beta, this sum of two currents, N1 and N2, the trace of two independent currents. Take p beta and just try to look at the derivative in beta of the probability that 0 is connected to the boundary of the box. So here, this guy, remember, you take two sourceless random current on the graph. So let's say we are on the box lambda n, and take the trace of this. So it gives you a measure, a percolation measure. Look at this quantity. Well, in fact, there is a proof which is, very similar to the proof for percolation, a little bit more complicated, which tells you exactly the following inequality. Times 1 minus probability beta of 0 connected to lambda n. So it's exactly the same inequality, except that you get a 2 over beta here instead of 1 over p. But otherwise, it's the same. The way you prove that, you use the random current. It is a little bit more cumbersome than here. But somehow here you had, remember, it was based on the pivotal points. You use Rousseau's formula and you get pivotal points. When you differentiate this quantity, you get typically the fact that in the current, you have this type of thing happening. You have a current going from 0 to some points, so you have sources like that. And you have sources here going to the gauss vertex, because, well, I don't want to go into detail, but there is a gauss vertex involved in the picture. So somehow you see the same kind of geometric quantities, except that manipulations are a little bit more tricky. But it's a two-page proof, and there is nothing, and completely self-contained. There is no huge difficulty, but it's less apparent than for percolation. Okay? Well, we are almost done, because what is the last thing we need to observe? Well, it's sufficient to observe that, by definition, this thing, at least if you take as currents guys that are defined on the graph plus the gauss vertex, this, I said, is just the square of the magnetization. Earlier I took the square of sigma x, sigma y, and I was telling you this was related to the probability for this current to be connected. If you take just sigma 0 and you take currents on lambda n union the ghost, what are you going to get? You're going to get the probability that 0 is connected to the ghost. And you can do something like that. So I don't want to go into details, but just, as an idea, to convey the idea that this thing is in fact just the square of the probability of the spin of the magnetization. But now you see, if you re-put in the differential inequality, you integrate, and then you use that it's the square here instead of the thing, you get exactly that. So it's this is the end of this sketch of proof. I agree. I mean, that's not even close to be a proof, but I mean, if you have 1 hour in front of you, that's basically what you need to present the proof. Nothing more. And it's really the same lines as for percolation, the same strategies as for percolation, for those who saw the proof. So that was the exponential decay for easing. You know, I mean, somehow these are the only cases where we know how to prove exponential decay. So it's kind of strange that the two only cases that we know for, I mean, there is exactly the same proof. How do you do for the other models? How, I mean, is there some geometric representation hidden somewhere that will have this type of properties and that the same proof works? We don't know. Okay, we enter in the last section, which is discussing the continuity of the phase transition. Okay. So that's the last theorem I want to discuss. And the theorem is going to be, I mean, the first statement is going to be a little bit strange, maybe. Theorem. So let's, I mean, just take ZD. I mean, D could be equal to 1. I'm taking long-range models. So one has to be, you know, I mean, in one dimension, it's also interesting. And so consider easing on ZD with some coupling constant, coupling constant as I defined before. And then the theorem is saying the following. If I take the free boundary condition and I look at beta critical, if I don't have ordering, meaning if I look at this quantity, so I look at the spin-spin correlation for the free boundary condition, right? If this thing tends to 0 as x tends to infinity, then, so this may be the case. Remember that then something very strange happens is that there is no ordering for the plus state. The free state and the plus state have no reason to be equal. Remember that for Q very large for the Potts model, for the random cluster model, there was, you know, non-uniqueness of the infinite volume measure. The phi 0 was not equal to the phi 1. So if you transfer that to the Potts model, that was telling you that the monochromatic boundary conditions for the Potts model have nothing to do with the free boundary conditions. These are completely different states. In fact, for the free boundary condition, you would have exponential decay of correlations at criticality, so you would have a property like that. But for the plus state, for the monochromatic boundary condition, you would have ordering. You would have spontaneous magnetization. Well, here, this theorem is saying this is not the case for easing. In the sense that, in fact, you can even remove let's put it. There is no ordering for the plus state if there is no ordering for the free state. So very different from the Potts picture for the nearest neighbor Potts model on Z2 or on ZD, by the way. So just a remark, a funny remark. No, it's not funny, but interesting one. So as I said, for Potts nearest neighbor, this is false in general. Just take planar model with Q very large. But here, for the easing model, there is something nice, is that so it's always true, yet the phase transition is not always continuous. So take D equal 1, so easing D equal 1, and take Jxy to be 1 over x minus 1 squared. So it's a one-dimensional model, except that you have long range. Well, this model has a discontinuous phase transition. So this is discontinuous. It's a result by Eisenman and a few other authors. I guess Chase and Newman. And, but it's not contradictory with this quantity, with this thing, because somehow what is going to happen is that you are going to have ordering for the free state, in fact, at criticality. So this type of phase transitions are very different from what you expect for nearest neighbor. For nearest neighbor, you really expect that if you have a discontinuous phase transition, somehow think of the free state as the limit from below. It's like it will look like the limit of the infinite volume measure from below. So in particular, you have exponential decay from below. And in fact, in this context, you are going to get that at criticality for the free state, there is still exponential decay. It's a very disordered model. It looks really subcritical. Think of the plus state, or the monochromatic state for Potts model, as a limit from above. And it may be, indeed, and it's going to be the case for discontinuous phase transition, that it's going to keep the ordering from above. It's not, the ordering is not going to vanish. So there is absolutely no reason why this free state, which is this limit from below, should coincide with the plus state from above. And in general, they don't. For the Ising model, somehow we are saying that they do coincide, and that if the phase transition is discontinuous, then the only way is that the ordering, the disordering from below gets weaker and weaker and really converges to some positive ordering at criticality. So it's completely different from the Potts model where it's going to converge to something highly disordered. It's just that, in fact, it has nothing to do with the limit from above. So it's completely different phenomenology for Ising. So for Ising long range in dimension 1 than from Potts models in nearest neighbor. So let's try to prove that. Let's try. Sorry. Now, what is the corollary of this? The corollary is that the nearest neighbor ferromagnetic Ising model on ZD for D larger or equal to 2 has a continuous phase transition which by this I mean that if I look at the magnetization at criticality, it is 0. So that's the equivalent for the percolation model of the fact that there is no infinite cluster at criticality. And let me just explain in a second how you deduce this from the other ones, for the other theorem. So you need to do something, since we saw that there are Ising models that have discontinuous phase transitions. And how are you going to do that? Well, we need to prove that there is disordering for the free state at criticality. And what is going to happen is that this, I'm not going to prove to you, but that's a famous theorem, which is saying the following beautiful thing, I think. It's called the infrared bound. It's not at all specific to the Ising model. And it's saying the following. There exists, for every beta, there exists a constant C, which is depending on beta only, such that if I look at the, let's take free state at beta, and I look at sigma 0, sigma x, or let's take plus state. No, free plus free. Free. So I'm going to take beta smaller or equal to beta critical. That would be simpler for the statement. Otherwise, I'm going to confuse everybody, myself included. So you take the spin-spin correlation. Well, it's bounded by C times the green function between x and y. So green function here is a green function. Sorry? 0 and x. You are entirely right. Sorry. So it's a green function. And here, what I'm going to do is, what do I do? No, that's, sorry. I did something wrong here. I'm looking at the nearest neighbor ferromagnetic Ising model. That's very bad. The green function of the simple random walk. So it's just the expected number of visits to x starting from 0. So you see that, I mean, in dimension 2 doesn't give you anything because this thing is infinite. But starting dimension 3 and more, it gives you something. Tells you that it decays. So in particular, it tends to 0 because the green function is, because the simple random walk is transient. So it's telling you that this thing is tending to 0 as soon as d is larger or equal to 3. So maybe here, as a corollary, it's only for 3. And for d equal to, we'd already proved last week that it was continuous. Notice one thing which is interesting is that this works for the nearest neighbor Ising model. But in fact, for a more general model, you can define the natural green function as well. So you can say, for general, this guy, you could take the green function of the random walk with jumps proportional, I mean with probability proportional, to jxy. So if you are at a point x, you jump to y with probability proportional to jxy. And as was suggested before, since we are, I mean, there is this hidden assumption that the sum of the jxy is going to be finite, otherwise beta c is 0. So you just you jump with probability jxy divided by the sum of the jxy. Okay? So you have a natural random walk associated to any model. And in fact, you expect this inequality to be always true. So now what does it tell you? It tells you that this theorem, that you have continuity as soon as the random walk associated to the model is transient. There is just, so this is at least how you should predict that it's continuous or not. I mean, that it's continuous. It's not an if and only if. It's just one thing is, in fact, to prove this, I'm not going to tell you how you prove this, but I'm not going to do the proof, but the proof is based on what we call reflection positivity. It's a very, very classical technique, which was introduced by Froelich, Simons, and Spencer. And unfortunately, it's not very robust somehow. So it works for nearest neighbor. It works, for instance, if you take 1 over x minus 1 to some alpha. So you can take long-range models. It works if it's exponential of minus the distance as well. But for some finite range model, for instance, it doesn't work so well. It requires first some symmetry, and second, a little bit more than that. There is some structure about the jxy which is non-trivial. But at least it gives you a hint of when you can for sure tell it's continuous. So I'm not going to prove that. It's based on reflection positivity, which is, by the way, a technique which is also used in quantum field theory. It's not specific to this case, but Froelich, Simons, and Spencer really introduced the technique in this context. Okay, I'm almost done, so I need to tell you how we prove this theorem. Sketch how we prove this theorem. So, we are going to try to work with the geometric representation. But what we are going to do is the following. So take n1. Remember, in finite volume, you take n1, sourceless current, on G, on a graph G. So that just means you sample it proportionally to W beta of n. Okay? Probability is proportional to this weight. You can take n2, but this time I'm going to take a sourceless current on G union the Gauss vertex. Okay? And now I just look at n1 plus n2, the trace on on G. Okay? I don't care about what is going on. In this guy, you have also this nx delta. Okay? There are these guys that are going to the ghost. Here it's really on G. Here is on G union the ghost, which I should have definitely called G, but anyway. I don't care about any of the edges between x and G. I just care about the edges in the plane, I mean in ZD. And I take the sum of the two, I take the trace, it gives me a probability measure, which I call PG beta. So it's not exactly the same as the one I introduced before. Well, let's put a tilde. It's not exactly the same as before, because here, one of the currents is on G union delta, not on G. Right? But, I mean, you can do that. And now you can take the limit. I mean, you need to justify why you can do it, but trust me, you can take the limit when G tends to ZD and get a percolation measure in the whole plane. So this percolation measure is translational invariant. It is in fact also ergodic, you can check that. It has also another property is that what is outside, you can always open an edge. You cannot always close an edge. That's weird, but you can always open. So we are going to say it's, I mean, so you have insertion tolerance in the sense that you can always insert an edge. It's fine. With, I mean, at positive costs in energy. So it's a little bit like for the random cluster model, this finite energy property, except that this time it works only in one direction, which is you can open, you cannot close. The reason you cannot close is because you see underlying there are these currents that have sources constraints. So maybe closing an edge would force the existence of two sources, which you don't want this to happen. So that's why you cannot always close, but whatever. Okay. By what do I start to try to do it? Okay. Let's start by that maybe. Yes. Let's look at this quantity. I look at the spin-spin correlation between x and y for the plus state. And I want to compare it. Let's put it in G first. So I mean, I compare it to the same quantity for the free boundary conditions. How can I write that? Well, this is a ratio of, it's a sum on random currents with sources x and y of W beta n1 divided by the sum on sourceless current of W beta of n1, right? I can do the same for this guy as well. Maybe I should have said that this should be, let's say this is n2 and this is n1. Okay, n1 is the one with the. So here, really note that because I have plus boundary condition, this n1 is really on G union the ghost. So I can do the same with this guy. This is just the formula I had before. And I get that. So now let's put everything together, the two terms together. So I'm going to get the sum of a sourceless current N1 and N2 of W N1, W N2. And here I get the sum N1 as sources X and Y, N2 as no sources of W beta N1, W beta N2. Okay, this is just because since I added this term, I add it at the top as well. And now I have minus the same quantity where this time the sources are for n2 and not for n1. So what do I do now? I'm just going to use the switching lemma. So I use the switching lemma, and using the switching lemma, what do I get? I get the indicator that x is connected to y. So if I write everything with these sources, I'm going to get a 1, which was the first sum. And the other guy, since I use the switching lemma, I get this quantity. So let's make a picture. So you have your graph G. You have x and you have y. So in one case, I mean, here this is just indicator that it's not connected. So I have n1 and n2, and not connected mean what? Well, I have sources between x and y. So I need for n1. So I need to have a path going from x to y, right? So this seems contradictory because I'm saying x and y are not connected. But why isn't it contradictory? Because n1 is on G union the ghost. So they are the sources at the ghost a priori. So just think of nearest neighbor. So for nearest neighbor, the ghost is only connected to guys on the boundary because the Jx delta is 0 inside. So what is the possibility? What is the way you are going to get that x is not connected to y? You are going to get that if x is connected to the boundary and then to the ghost, and y is connected to the boundary and then to the ghost, and these two guys are not connected. This is exactly the only possibility. So when G tends to infinity, what do you get? You are going to get that x and y needs to be connected to infinity, really, in this thing. So the only problem is that this is still not a probability measure, because here the sources are not the same as here. It's not sourceless currents. But what you can do is, by paying a finite cost, I can open edges, and I can open a path like that between x and y to remove the sources. But what remains? I still need x to be connected to infinity. So this quantity here, overall, is smaller when G tends to infinity, or I mean even when G, let's say when G is finite, this is smaller than a certain constant, which is the cost of adding this red thing. Here, I mean, of course, I need to justify this, but I mean, you can trust me that you can do it at a cost like that. And then I have the probability for G beta that x is connected to the boundary, I mean, to the ghost, basically. Okay? When delta tends to infinity, this is bounded by constants times the probability at beta that 0 is connected to infinity, in fact. When G tends to infinity, to ZT. Just think of nearest neighbor, okay? X is connected to the boundary. If I let G tends to infinity, it's going to tell me that X needs to be connected. So X is going to be connected to infinity. So how will I mean, if I can prove that this quantity is equal to this one, what would, so imagine I can prove that there is no infinite cluster for this weird percolation measure. Then I will have that this quantity is equal to this quantity which tends to 0 by assumption when x and y, so let's put 0 and x maybe to recover the, tends to 0 when x tends to infinity. Okay? But now this quantity by the second Griffiths inequality, it's larger or equal to just sigma 0 squared, the spontaneous magnetization squared. This is the second Griffiths inequality. So if this tends to 0, that tells me that this is equal to 0. So what I need to prove is to prove to you, to convince you that there is no infinite cluster for these strange measures that I defined. That's a p tilde here for this measure. Okay? So notice that somehow all what I did here was kind of useless up to now, because I already had an interpretation with the random cluster model. I could have said, take the random cluster model with wired boundary condition. If I can prove that there is no infinite cluster at criticality for this guy, I'm going to get exactly, because this quantity is exactly the probability for the random cluster measure with wired boundary condition that 0 is connected to infinity. Then if I can prove absence of infinite cluster for this guy, I'm done. So why did I gain? Because this measure, I can definitely trust me that this measure is much worse than the random cluster measure to study. It doesn't have FKG type inequalities. It's very difficult to study. So here it seems like we didn't do anything smart. But now we still didn't use our assumption. We use it at the very end, but somehow we could use it before. We could use the fact that this quantity is tending to 0. So let's try for a moment let's just try to look at this quantity. What is the probability tilde at beta that 0 is connected to x? So this is exactly, let's write slowly. It's the sum. So this is a partition function. Well, that doesn't make sense in infinite volume, but just put a g if you prefer here, and that would be fine. Or let's put the g. Okay. And here I get sum of the weights. And here I get the indicator that 0 is connected to x in n1 plus n2. Okay. Now I'm going to use, because that's the only tool we are using anyway, the switching lemma to remove this indicator. What do I get? I'm going to get the sum. So I'm going to have sources 0 and x and 0 and x. So what do I get? I get one of the guys is going to be mu g beta 3 sigma 0 sigma x. And the other guy is going to be the same with plus. Just remember that n1 is defined on g union delta and n2 is defined on g just. Okay? So you get exactly this relation. Sorry, we don't see with... but this is smaller or equal to that. And that by inception tends to 0. So you can let g tends to infinity, and then let x tends to infinity. This is tending to 0 when g tends to zd and x tends to infinity. So this tells me something strange. It's telling me that the probability that 0 and x are connected to each other is tending to 0. So here, a priori, you think, OK, I'm done. If I have an infinite cluster, since I'm translational invariant, then the two guys have, they are going to be in the infinite cluster with and ergodic is going to be in the infinite cluster with probability tending towards just the square of being in an infinite cluster. Okay, they both are in the infinite cluster with positive probability bounded away from 0. The only thing is that it may be that there are more than one infinite cluster. It may be that there are infinitely many infinite clusters. So, OK, both guys are in an infinite cluster with probability not tending to 0, but they are not necessarily in the same infinite cluster. Okay? And since the model is very strange, there is no reason a priori that it could not happen that you have infinitely many infinite clusters. Yet, I presented this Burton-Keane argument not for nothing. What did we use in the Burton-Keane argument for Bernoulli percolation? We use the fact that you have translational invariance. We use ergodicity. Well, both things are OK. And we use finite energy. Here, it's not finite energy. It's insertion tolerance. But you can easily check that this is a sufficient property to run the Burton-Keane argument. So the Burton-Keane argument is going to work here. You need to redo it, but it works. And what you get, so Burton-Kin argument, works, and you get that so there exists a unique infinite cluster almost surely if it exists. I mean, so almost surely if it exists. And so therefore, that tells me that this quantity cannot tend to 0 if it exists, if there is an infinite cluster. So you see that was the last piece of the puzzle, was to prove that you don't have infinitely many infinite clusters. Since you don't have, this quantity doesn't tend to 0 if there is an infinite cluster, so since it tends to 0, that means there is no infinite cluster. And if there is no infinite cluster, when you go there, you get that the spontaneous magnetization equals 0 at criticality. Okay, so that was the end of this proof. And that's also the end of the class. So basically, I hope I managed to convey a few nice ideas and the fact that there are connections between all these models. If not direct connection, there is a connection in the techniques that you use to solve these problems. And that if you want to study these a priori very analytic models of spin, spin models on spin lattice models, well, it may be very interesting to go through this geometric representation, and there, basically, probability kicks in, integrability kicks in when you look at the loop models. I mean, you have different, combinatorics, you saw that there are many things that come from combinatorics in the proof, and other things that come from analysis, for instance, this reflection positivity is a purely analytical consequence. So you have many fields that are entering in this area, and one of the important ideas that you should keep in mind is that there are several geometric representations for the same models. Here I just described a few, but there are many others. High, low temperature expansion of the Ising model, loop representation of the ON model, for instance. You have a random walk type representation. So this random current has also another, we can look at it another way and look at it as random walk in random environments. You have many representations that I didn't describe, and somehow you need to choose the right one for your problem. I mean, they are suitable for different problems, and you need to choose the right one. Well, thank you very much. I mean, it was a pleasure for me to give this class, and thank you for coming. And see you soon.